So, what exactly happens when we try to merge the colossal forces of gravity with the minuscule world of quantum mechanics? A gravitational singularity, space-time singularity, or simply singularity, is a condition in which gravity is predicted to be so intense that space-time itself would break down catastrophically. As such, a singularity is by definition no longer part of the regular space-time and cannot be determined by where or when. Gravitational singularities exist at a junction between general relativity and quantum mechanics. Therefore, the properties of the singularity cannot be described without an established theory of quantum gravity. Trying to find a complete and precise definition of singularities in the theory of general relativity, the current best theory of gravity, remains a difficult problem. A singularity in general relativity can be defined by the scalar invariant curvature becoming infinite, or, better, by a geodesic being incomplete. Gravitational singularities are mainly considered in the context of general relativity, where density would become infinite at the center of a black hole without corrections from quantum mechanics, and within astrophysics and cosmology as the earliest state of the universe during the Big Bang. Physicists have not reached a consensus about what actually happens at the extreme densities predicted by singularities, including at the start of the Big Bang. General relativity predicts that any object collapsing beyond a certain point, for stars, this is the Schwarzschild radius, would form a black hole, inside which a singularity, covered by an event horizon, would be formed. The Penrose-Hawking singularity theorems define a singularity to have geodesics that cannot be extended in a smooth manner. The termination of such a geodesic is considered to be the singularity. Modern theory asserts that the initial state of the universe, at the beginning of the Big Bang, was a singularity. In this case, the universe did not collapse into a black hole, because currently known calculations and density limits for gravitational collapse are usually based upon objects of relatively constant size, such as stars, and do not necessarily apply in the same way to rapidly expanding space such as the Big Bang. Neither general relativity nor quantum mechanics can currently describe the earliest moments of the Big Bang. But in general, quantum mechanics does not permit particles to inhabit a space smaller than their Compton wavelengths. Many theories in physics have mathematical singularities of one kind or another. Equations for these physical theories predict that the ball of mass of some quantity becomes infinite or increases without limit. This is generally a sign for a missing piece in the theory, as in the ultraviolet catastrophe, renormalization, and instability of a hydrogen atom predicted by the Larmor formula. In classical field theories, including special relativity but not general relativity, one can say that a solution has a singularity at a particular point in space-time where certain physical properties become ill-defined, with space-time serving as a background field to locate the singularity. A singularity in general relativity, on the other hand, is more complex because space-time itself becomes ill-defined, and the singularity is no longer part of the regular space-time manifold. In general relativity, a singularity cannot be defined by where or when. Some theories, such as the theory of loop quantum gravity, suggest that singularities may not exist. This is also true for such classical unified field theories as the Einstein-Maxwell-Dirac equations. The idea can be stated in the form that, due to quantum gravity effects, there is a minimum distance beyond which the force of gravity no longer continues to increase as the distance between the masses becomes shorter, or alternatively, that interpenetrating particle waves mask gravitational effects that would be felt at a distance. Motivated by such philosophy of loop quantum gravity, recently it has been shown that such conceptions can be realized through some elementary constructions based on the refinement of the first axiom of geometry, namely, the concept of a point, by considering Klein's prescription of accounting for the extension of a small spot that represents or demonstrates a point, which was a programmatic call that he called as a fusion of arithmetic and geometry. Klein's program, according to Born, was actually a mathematical route to consider natural uncertainty in all observations, while describing a physical situation by means of real numbers. In our exploration of singularities, it's essential to understand that not all singularities are created equal. Singularities can be categorized into different types, each with unique physical features and characteristics relevant to the theories from which they originally emerged. Let's start with conical singularities. A conical singularity occurs when there is a point where the limit of some diffeomorphism invariant quantity does not exist or is infinite. This means space-time is not smooth at the point of the limit itself, creating a cone-like structure around this point with the singularity located at the tip. An example of such a conical singularity is a cosmic string or a Schwarzschild black hole. Next, we have curvature singularities. Solutions to the equations of general relativity or other gravity theories often result in encountering points where the metric blows up to infinity. However, many of these points are regular and become infinite only due to an inappropriate coordinate system. To test for a singularity, one must check if diffeomorphism invariant quantities, such as scalars, become infinite. For instance, the Schwarzschild solution describes a non-rotating uncharged black hole, where the metric becomes infinite at the event horizon. But by changing to another coordinate system, like the Kruskal coordinates, the metric appears smooth. However, at the center of the black hole, the metric suggests a true singularity exists, confirmed by the Kretschmann scalar becoming infinite. More intriguingly, we encounter naked singularities, which defy the cosmic censorship hypothesis. Until the early 1990s, it was believed that general relativity hides every singularity behind an event horizon, making naked singularities impossible. However, simulations by physicists Stuart Shapiro and Saul Tucholsky indicated that general relativity might allow for naked singularities. These objects remain theoretical, and their true nature is still unknown. Lastly, consider singularities in rotating black holes, known as Kerr black holes. Here, the singularity occurs on a ring, known as a ring singularity, which may theoretically become a wormhole. Similarly, disappearing event horizons can occur in the Kerr metric if the angular momentum is high enough, or in the Reissner-Nordström geometry of a charged black hole if the charge is high enough. As we journey further into the enigmatic realm of singularities, we must address a groundbreaking concept that reshaped our understanding of black holes' entropy. This idea, introduced by the brilliant physicist Stephen Hawking, revolutionized our perception of these cosmic giants. Before Hawking's groundbreaking work, the notion of black holes having entropy was largely ignored. However, Hawking radiation changed everything. This phenomenon demonstrates that black holes radiate energy, conserving entropy and resolving the apparent conflict with the second law of thermodynamics. But what does this mean for the fate of black holes? Entropy, by definition, implies heat, and therefore temperature. Hawking radiation suggests that black holes lose energy over time, hinting that they do not last forever, but instead slowly evaporate or decay. This loss of energy is intricately linked to a black hole's temperature, which is inversely related to its mass. Interestingly, all known black hole candidates are so massive that their temperatures are far below that of the cosmic background radiation. This means that, rather than losing energy, they gain it by absorbing this ubiquitous radiation. Only when the background temperature falls below the black hole's temperature, a scenario predicted to occur at a cosmological redshift of more than 1 million, will black holes begin to lose energy on net.